Today, we're going to start section 5.2 and study exponential growth and decay relationships. Most of these will be applications that produce exponential growth or decay equations, and some will be standard exponential equations that we have to solve. First example is one that we've already studied. We're just going to continue working with this concept. We studied it the first day of section 5.1. And it reads, suppose a car presently worth $8,200 depreciates 20% per year. About how much will it be worth 2 years and 3 months from now? So you have to read this carefully. And the key word here is the word depreciate, right? So that means it's going to decrease in value 20% each year. So that's an exponential decay model. So back in section 5.1, we learned about the exponential growth and decay models, where A of t is the overall value or output. A sub 0 here is the initial value, the starting value. 1 plus the growth rate, where R is a numerical value and not a percentage, and T is the time. And this unit of time here should match the unit of the growth rate. Decay, excuse me, this should say decay. K can be modeled by a similar function, A of t equals A sub 0 times quantity 1 minus R to the t. Again, it's careful that you read whether it's a growth or a decay scenario. So to get started here, we're going to identify it's a decay, and we're going to use this standard equation. A of t equals A sub 0 times quantity 1 minus R to the t. So things we need to identify, right? So it's presently worth $8,200. That's going to be your A sub 0 value. It's depreciating at 20% per year. So we're going to convert 20% into a numerical value of 0.20. And that's going to be our decay. And about how much will it be worth in 2 years and 3 months, right? So this is our time. The key thing, too, when you're looking at this is you always want to make sure that the unit of measure you're going to use for time matches the unit of time measured in the growth or decay rate listed right here. So we have A sub 0 is 8,200. Our R value is 0.20, and our T value is 2.25. Be careful. 2 years and 3 months is not 2.3 years. 3 months out of 12 months in a year is 1/4 of a year, or 0.25 years, giving us a time of 2.25. And at this point, it's take these three values, drop them into our relationship here, follow the order of operations, and use your calculator to produce an approximate value here. This is the dollar amount, so we would naturally round to the hundredths place unless it's stated otherwise. So when we're using the order of operations here, it's 1 minus 0.2 first, which is going to leave us with 0.80. And then we have to raise it to the 2.25 exponent or power. And then we multiply by 8,200, produce $4,963.25. This is all going to be done on your calculator. So when you're showing work for this, it's key that you off on the side, identify these values, and you definitely set up the exponential decay model with the values inside it before you produce a final answer here, right? So, and then clearly we should write, the car will be worth $4,963.25 in 2 years and 3 months, right? All right, so let's try another example. A house bought 5 years ago for $100,000 was just sold for $135,000. To the nearest 0.1%, what is the annual growth rate? Okay, so no tricks here, but you're definitely going to have to use a little bit of algebra to solve for the growth rate, as opposed to just throwing all the values in the formula and evaluating it. And again, we have to identify some critical values here, right? So this is an exponential growth, where we're going to use the growth formula. And I know it's a growth because the house was bought 5 years ago and now it's $135,000. So it's increased in value. And then that increase is usually considered exponential. So moving on, we have a a little unique situation where we're given the A of T value. We're given the output value, the final value of the house, which is 135,000. We're also given the initial value, the A sub 0 value, which is $100,000. We have one more value too. It's our time. So time is 5 years. So T is 5. And at this point, we have three values. If you look at the relationship here, we have one for A of T, one for A sub 0, one for R, and one for T, giving us four values. Anytime you have three of those four values, you will be able to solve for the missing value here, right? So it's pretty basic for all the missing values, right? So if we have to solve for A of T, that's easy. A sub 0 is pretty basic. R is pretty basic. Solving for T is a little complicated, and we'll get into that later. But for now, I'm going to take my three values and drop them into this relationship right here. So 135,000 equals 100,000 times 1 plus R to the fifth power. Solve it just like an equation. Our goal is to isolate R, so we have to break it down in reverse order. First thing we need to do is remove the multiplication of 100,000. So we divide both sides by 100,000 here. And this simplifies nicely to 135 over 100 right here, right? And then once that is isolated, what remains on the right is here in blue, 1 plus R to the fifth power. Now, this is a little different. You may remember from Algebra 2, you may not. But our goal right now is to solve for R. So what we have to do is separate the exponent here from the quantity 1 plus R, right? So if this was an exponent of 2, you would take the square root of both sides. It's an exponent of 5, so you can take the fifth root of both sides. And you can use your calculator to do that. Taking the fifth root is going to isolate 1 plus R, right? It'll undo this exponent of 5. And over here, you take the fifth root of 135 over 100 in your calculator. Don't round too early. I would go to, more than the hundredths place, so the thousandths place or the 10,000ths place works. And the technique I want to show you here, though, is instead of taking the fifth root where you actually, you put the radical on top of the equation or over the equation. Since we're working with exponents here, what we can do is we can raise both sides of this equation to a fractional exponent. Just like we can square both sides of an equation or take the square root of both sides of an equation, right? And remember, we would take the fifth root here. So the fifth root is also an exponential relationship to the 1/5 power. And here, that's what I'm doing, right? So what I want to do is raise this to an exponent where the denominator of this exponent is going to simplify with the exponent in the original part of this equation here. So 5 times 1/5 is 1, and that undoes it. That's just like taking the fifth root. Over here, we drop this into our calculator, and then from there, what we're going to do is we need to just now solve for R, right? So I'm going to subtract 1 from both sides, and now I'm left with 0.0619. But what we want is the to the nearest 1/10 of a percent. What is the annual growth rate? So this is the numerical version of that form. To convert it into a percent, we're going to multiply by 100 here. And that'll turn us into, when we round to the nearest 10th, 6.2% growth per year. It's critical that you remember to multiply by 100 here.